are missing there. So please stop by, and now I can give you more. And the second announcement that I am asking Stein, Solberg, Volkov, Sage, Madsen, Tyler, Blanc, and Hiller to see me before the end of the day.
Hi, good morning. So the banquet is going to be next Thursday, and we really need as accurate as possible number. So I'm going to put a piece of paper there. I thought I brought the list of participants so everybody can check, but I'm incompetent and I forgot it. So I'll bring a piece of paper and please write your name. By the way, the banquet is included in the registration fee, so you don't have to pay. So please check there. If you have a guest, the guest had to pay, but that you took care of it with Ms. Canino. So, but write down if there is another thing. So, in this way we'll have an accurate number. Thank you very much.
And the first speaker is Amiot from Université Grenoble Alpes, and the title is different than what I have here. So originally the title said cluster categorification and applications to building theory, but the title is derived invariance for surface cut algebras.
Yeah, sorry, but first I have a problem with the microphone. Sorry. Oh. One is given as a very nice topological description. So to each surface with mark points, one can associate such category, and we have nice topological tools to describe this category. And for my second talk yesterday, I show you how it's possible to construct from an algebra of global dimension tool also to Calabi-Yau category with nice properties, and among these nice properties we have this notion of gradient mutation, and we have results about derived equivalence. So my aim today is to understand what's in the middle to profit from both sides, I mean topology and derived equivalence. So the first thing I will show you, which is not something very difficult to see, but it's in fact the picture looks like this. So my problem is non-empty. I mean, for any surface, it's possible to find. So this class of categories are in fact categories coming from algebra of global dimension. And then I will show you how to apply my result with Opperman about derived equivalence to these special algebras that are called surface cut algebras. Okay, so let me remind you the setup. So we start with an oriented compact surface with mark points. So I would call G the genus, P is the norm of boundary contour. components, P is the number of punctures, and C is the number of mark points on the bundle. And if I fix a triangulation such that any puncture at valency and at least 3, then I can construct a quiver with potential, Q delta S delta. And remember that in that case, it's not hard. This quiver is nicely described because it's adjacent to the quiver of delta. And now, for my second talk, so I start with an algebra global, I mentioned 2, and one also can construct a graded quiver with potential that I was denoted by. Okay, anyway, so it's yeah, Q pi lambda W pi lambda D, and in this construction, so we have new arrows in the quiver, and these new arrows correspond to gradation, and they have degree 1. And my potential then is a potential which is homogeneous of degree 1. So what I would like, if I want from delta to construct such an algebra lambda, what I would like is what I call a cut. So it's a map from the set of arrows of Q delta to 0, 1, and making this potential homogeneous of degree 1. And remember, this potential, we have two kind of terms. The first kind of term is just given by, for each internal triangle, we should just, we have the sum of internal triangles. So here I just want these two up to 1, so I just have to select one or one to 1. And we have also second kind of terms. So around each puncture, I have an oriented cycle in the quiver, and this is a term of the potential. So I also want this to have degree 1. So I have these two conditions. So the first easy remark is that it's possible to construct cuts where triangulation where such cut does not exist. So this, so of course if you don't have punctures, so you don't have this condition, well, only with this condition, of course, any triangulation will admit cuts, but if you ask these two conditions, then you may have troubles. And yeah, I will add another condition, which is condition 3. I will also ask that if I have a triangle here, and such that one side is a boundary segment, so then I just have one arrow in my quiver, and I ask this arrow to have degree 0. So I won't explain exactly this condition, but so the first result, it's not something not so difficult to see, but for any surface, it's easy to construct a valency greater than 3 triangulation and a cut satisfying the 3 conditions. So not all triangulation have cuts, but at least for any surface you can find a triangulation and a cut. And so this, leads me to this definition. So we start with a valency greater than 3 triangulation and a cut satisfying these conditions. So then the corresponding what I call a surface cut algebra will be the degree 0 part of. So from this cut I get this Jacobian algebra. This Jacobian algebra is graded because the potential is homogeneous of degree 1. And I take the degree 0 subalgebra of this algebra, and I call this algebra a significant cut algebra. So just let me show you how it works. It's not difficult to understand what this algebra is. So this algebra is given by quiver with relation. So the quiver, so Q0, the quiver And the set of arrows, these are just arrows of degree 0, so they correspond to angles of degree 0 in the triangulation, because I just take the degree 0 subalgebra. And the relations, so for each internal triangle, I have one arrow of 1. And so if the puncture, if the marked point associated to this arrow of degree 1 is on the boundary, then I have a zero relation with alpha 0. And if the marked point corresponding to the arrow of degree 1 is a puncture, then I get a commutativity relation as here. So just let me show you a complete example. So I start with the annulus, where I have two marked points on each boundary component, and I take the triangulation, so this one. And so in this triangulation, so here I don't have punctures, so I don't have really I have no problem to find a cut. So first I have to select one to see what are the internal triangles. And here I just have one internal triangle, here it is. And in this internal triangle, I just have to select one angle and put Q1. So let's try with this angle. I put Q1, and then my algebra is given by this quiver, so which is just the adjacency quiver where I delete this arrow of Q1. And then I have one relation, which is the composition of the two pink arrows, which is 0 because they are in the same triangle. Okay. Maybe a more complicated example. So, yeah, this is just, sorry. So this is just an octagon with two punctures. So here is a triangulation. So, and yeah, if I take this cut, so this is a valency plus 3 triangulation, and this cut is actually a cut satisfying 1, 2, and 3. So you just have to check that for each internal triangle, I have one blue angle, and for each puncture, I have one blue angle also. And also, I have, so you can see like the very upper triangle, the angle is not set. So it's fulfills this condition 1, 2, and 3. And the corresponding algebra, so it's given by this quiver, and the dots correspond to relations. So for instance, I have a commutativity relation, so the composition of the pink arrows is corresponds to this red path, like straight, and so on. So, okay. Yeah, so let's start with some results about this algebra. So we start with the surface cut algebras, and then first of all it has global dimension smaller than 2, and also it's tau to finite, and finally there is a triangle equivalence, so this is what we want, between the cluster category associated to lambda and the cluster category associated with a surface. And this triangle equivalence sends pi lambda to this, the triangulation we started with. Okay, so here, yeah, I should mention that, okay, so this last statement, it's, it comes from the fact that, well, I didn't explain you yesterday, the day before yesterday, I didn't explain you how really these categories are constructed. But in fact, these two categories, these two cluster categories, they are constructed in a very similar way. So it's not so difficult to see that actually they are equivalent, even if with the description that I gave you, it's not clear at all that they are the same categories, but in fact it's enough to check that the quiver with potential coincide, and then automatically you get the same category. So it's, once you know that, this third point is not so difficult to check. So that also the first point, I just show you an example to show you that it's not so clear that it's of global dimension 2. So this is an example of a code where the corresponding algebra is global dimension 3. And so this is the algebra, so it's given by the quiver, and here you have two overlapping zero relations, so you know that this algebra is global dimension 3. But this code does not satisfy this condition 3, so it just gives you an idea why we have this condition 3. So in fact, it's not necessary. I mean, you can find codes with condition only condition 1 and 2 that satisfy this proposition. And so 3 condition, it just means that for a triangle of this shape with one boundary side, you don't want this arrow to have the good one. Yeah. What? 1 and 2 is just to have the potential homogeneous optical one. So you want in each triangle you want just one angle, and for each puncture just one angle. These are really necessary, but the third one is not necessary. Yeah, so now before stating the main result, I have to define something. So I denote by I1 free of S minus M, the set of oriented closed curve on S minus M, modulo free homotopy. So free homotopy is just homotopy, but you don't care about the base point. Okay. And we have the following proposition that the degree map B yields a well-defined map from this set to Z. And I will explain you how it works. But this is nice because now, I mean, the degree map D, of course, it's a map that depends on the triangulation. But now you get something, D bar, which does not depend on the triangulation, which is just something related to the surface. So this is the main point. So how we construct this map D bar is very easy. You just, so I show you in an example. So I take the triangulation here. I take a curve, so a closed curve on my surface, and I see how it crosses the different triangles. So here you can see that this red curve crosses this angle, and then you can just, okay, if the degree of this was degree 1, then the degree got by 0, and if I have selected this angle, then the degree is 1 or minus 1 depending on the orientation of the curve. So then you can imagine how it works to construct this map. But the main point is that it's really a well-defined map. Okay, so here is the main theorem. So I start with 2 surface cut algebras, and then I get the following equivalence. So dB lambda is equivalent to dB lambda prime if and only if there exists an orientation preserving homomorph from S to S prime that also preserves So if I compose d prime bar with non-homomorphism, I still get a map from pi 1 3 of s minus n to z. So I can just compare these two applications. So this theorem, as you can imagine, this theorem uses strongly the theorem I had with Opperman. But here, the nice point is that now we have an equivalence. So it gives you a complete criterion for derived equivalence for these two algebras. So this is the first point. And also, what is nice here is the fact that to check that two algebras are derived equivalent, you don't have to, so concretely, you don't have to exhibit a sequence of mutation to pass from 1 to 0. So this point 2 is just direct criterion. So, because we don't have to. But yeah, of course, it's not so direct because you have to find this homomorphism phi, which was not so easy in practice. But at least, I mean, just in the statements, it's nicer. Okay. So yeah, just we go back with the example. So I start with again with the analysis with 2 mark points on each boundary component, and I take this triangulation. So this triangulation is not the previous one. So this triangulation, in this triangulation, I don't have any internal triangle. So my cut has to be 0. Right. So then I get just the path algebra of this quiver, which is asymptotic. And yeah, and then my degree map is 0, so this map D bar is also 0, of course. And then it should be 0 up to any homomorphism of the surface. So now let's do a flip at the arc 1. So if I flip this triangulation at arc 1, I obtain another quiver. And again, this triangulation does not have any internal triangle, so I don't have any problem here. Any choice with a cut or whatever. I mean, and so this is just the example I gave you yesterday. You start with an asymptotic quiver without relation. You perform the reflection at the vertex, and this is just Hafner's theorem. You get these two algebras are derived equivalent, and yes, they are derived equivalent because the corresponding maps are D bar are 0. And then maybe the first remark about the theorem, it just implies automatically that if you start with different surfaces, then of course you will get different derived categories. So, for instance, if I make an analysis, but now with 3 mark points on one and 1 on the other, I find what you know what I find. I find also the path algebra of type 8 tritilla, but with another orientation, and so these are not derived equivalent. So I have the theorem. So now, real example. So here I take the triangulation I had before, and I have 3 possibilities for my cut. So I can select either this angle, or this angle, and I get these different degree maps for the curve in red. Here, so it's either 1, 0, or 0. And then the theorem implies that the corresponding algebras are or are not derived equivalent. So these two are not the right equivalence because these two degree map are different. And while up to homomorphism, you cannot send non-zero degree map to a zero degree map. So it's just here it's easy to really check this experiment. Okay, so now let me tell you something about the proof of this result. So, yeah, I have two main ingredients in the proof. So the first one is given by this proposition. So we start with the graded tagged triangulation. Yeah, I didn't mention what the graded triangulation is. So graded triangulation is a triangulation such that the corresponding potential is homogeneous of degree 1. But here we don't ask the errors to have degree 0 or 1. You can have errors of degree 2 or negative degree. But if you start with a triangulation with a cut, and if you perform graded mutation, then you might get errors of higher degree or negative degree. So it's just, but if you start with a triangulation with a cut, and if you perform graded mutation, you always will get graded triangulation. So the potential will always homogeneous of degree 1. So we start with such graded type triangulation. And I take an arc, and then by this result due to Labardini, we have right equivalence. So I say that the flip corresponds to mutation, but more precisely, it says that if you do the Dax-Weimann-Zelinsky mutation to Q delta S delta, and if you compare this QP with the quiver with potential associated to the flip of this triangulation, you get a right equivalence. And the result is that this right equivalence is graded with respect to the grading mu IL of D. So this result is almost trivial in the case where you don't have puncture, because in that case this right equivalence is very immediate somehow, and you can just check that it works, it's graded, and that's okay. But in the case where you have puncture, then it starts to be much more tricky. I mean, the Labardini's proof is really, really technical to prove this equivalence in total generality, and then you have to check, like case by case, that it actually works. So it's much more work here. But as a consequence of this proposition, then it just says that somehow we can forget the potential. So if you start with a graded triangulation, you can just perform graded mutation or graded flip. So you keep track of the quiver and of the grading, and at the end you know that the potential you get is the right potential. So it's just you can totally forget this story about potential, which is a good thing because it's definitely by Weimann-Zelinsky procedure it's not so easy to do it. And so the second ingredient of the proof is this proposition. It says that one can pass from two graded triangulation, delta D and delta prime D prime, by a sequence of graded flips, if and only if, in fact, these degree maps are the same, like when you see them as maps from P and P1 3 to P1 2. So this proposition, yeah, maybe if I write something on the board, you won't see, but okay. So at least one direction is not so hard to check, because it's not difficult to check that if you just perform one graded flip, then you won't change the grading. one is the surface cut algebras are derived equivalent, and two is there exists an homomorphism on the surface. So we start here, so we assume that there exists an homomorphism of the surface such that the degree maps are the same. So now if we so just applying proposition 2, we get directly that the two graded triangulation has to be related by a sequence of flip. And if they are related by a sequence of graded flip by proposition 1, it means that the corresponding graded mutation of potential, that you have a sequence of graded mutation linking the corresponding QPs, and then you can just apply my result with Stefan, and you get the two algebras are directly equivalent. So this direction is almost immediate once you know this fact. So the second one is the one I want to explain to you. So we start with an equivalence from P lambda to P lambda prime. So this will give you such a commutative diagram. So here, all functors are triangulated functors, and this capital F will also be an equivalence here. And, okay, and what do I know? I know also that, so that lambda prime is sent to this triangulation delta prime, and moreover, it yields a grading of this triangulation, which is called d prime. So now what happened to lambda? So lambda is sent through this composition to something in C2 lambda prime. And this something is a cluster tipping object. Because F is an equivalent. So it's a cluster tipping object, so it should be a certain tagged triangulation. I call this triangulation delta second, and now I know that there exists a sequence of flip going from delta prime to delta second. And what I do is just I take the same sequence of flip and I apply the sequence of flip up there to lambda prime. I apply graded mutation in the derived category. And I get an object T. And this object has to be a pre-image of delta second. Because of what I said yesterday, because graded mutation upstairs corresponds to mutation of cluster tipping object downstairs, and mutation of cluster tipping object downstairs corresponds to flips. So then you should have such a thing. And now we have a pre-image of delta second. So we automatically get, from this pre-image, we get a grading, which I call D second. So it's a grading on this triangulation delta second. And I have also another pre-image of delta second, which is just F delta, because this big diagram commutes. So F delta is another pre-image of the same circle. So this implies that the degree are the same, but you have to compose with this isomorph. So finally, you get really that D composed with phi is the same as D prime, and you end up by an argument due to those, right? Due to Bridge and Smith, would say that if you have an isomorphism between two Jacobian algebras coming from type triangulation, then this isomorphism in fact comes from an homeomorphism of the surface. And yeah, this is we have to adapt just a little bit this proof to get the grading, but this phi induces an homeomorphism of the surface, and we have this property. So this ends the proof. Okay. So this is how it works. So now I will explain you a bit of applications and consequences. So the first thing here is that if we really want to understand this derived invariant, what we have to understand is the action of the group of homeomorphism of the surface on this set, which is phi 1, 3, s minus 3. And while this group and this set are both kind of very ugly if you have a surface with positive genus. So in fact, the statement of the theorem is nice, but it's really hard to apply in practice. But however, we can use things. So let me show you a first consequence. So we start with such a surface, and I will take a very special curve on the surface, just this one. So this one is just a curve surrounding one boundary component with 3 mark points. So what can we say about this curve? So we can say that this curve is a separating curve. So it cuts out my surface into 2 connected components. And one of these connected components is just an annulus. It's just this annulus. Here, it's just an annulus with 3 mark points on the boundary. So if I apply any homomorphism to the surface, the image of gamma I should be a curve with the same properties, and a curve with the same properties would be also a curve like surrounding a boundary component with 3 mark points. So here we can deduce from this fact that if we just consider the collection of d bar gamma I and ci, so where ci is just the number of points, mark points on the boundary component. So for each boundary component, so for I going to 1 to b, so b is the number of boundary components. So for each boundary component, I just compute this, and this collection should be, is a derived invariant of this surface curve algebra. And actually, it's a derived invariant which is known. So we have the following proposition. So in the case where the surface does not have any punctures, this collection is more or less the AG invariant. I mean, it's more. In fact, this is this collection, but you have just to change it a little bit. But so this collection is an invariant which was described by Amiot and this guy. So this AG is not the same as this AG. But okay, sorry for that. So yeah, well, the fact is that when the surface does not have any punctures, then the surface curve algebra is always gentle. And for gentle algebras, there are lots of derived invariants that already exist, and in particular two abelian luminous guys. And okay, this invariant we can interpret in the case of surface algebras like this through this result. But yeah, this corollary works also with surface with punctures. So somehow here we get a generalization of this abelian luminous guys invariant. We get a new invariant for these algebras which are not gentlemen. Okay, so this was the first remark. So the second thing is that, okay, so what is this set, pi 1 free of S minus M? So in fact this set, it's not a group, it's the set of conjugate classes of the fundamental group of the surface. So it's not a group. This does not have any nice structure. But then still we have a natural application from this set of conjugate classes into the abelianization of the fundamental group, which is just H1 of the surface. But unfortunately, this map D bar does not factor. So it's not a group of homomorphism. It's not. This map D bar is bad. So this is one reason why we get trouble. But however, we have something. So if we take two different weightings, and even coming from different triangulation, if we do the difference between two such maps, then we get a factorization, and we get even more. We get a factorization through this group H1 of S. So here it means that, so yeah, just to be clear, what the difference between H1 of S and H1 S minus M. So in here, if I have a curve surrounding a puncture, well, it's contracted, but up there it's not. So this one is much bigger. It's something of rank 2b plus b plus b minus 1, and this one is just a free group of a free abelian group of 2b plus b minus 1. So here you don't care about puncture, and the reason is very simple. It's just because if you take a curve surrounding a puncture, then the degree of this curve has to be 1. It's just in the definition because the conjunction is homogeneous of degree 1. So the degree of this curve is 1, but then if you do the difference, because you get 0, then you get factorization. And also, I mean, why also this works is the same for if you have an inclined triangle, the sum of the degree of the angles is 1, which is something bad if you want to pass the homology, but if you do the difference between two gradings, then you get 0, so then you can factor this. So this is something important to remark, because as a consequence, it implies that if you want to compare two gradings, you don't have to compare them on the whole set I1 free of S minus M, which is really, really big, but just you can take a set of curves which generate this group. So you just have to select 2g plus b minus 1 curve, and we check that the degree coincide for these two curves. So as a consequence, if G0 and B is 1, so if G0 and B is 1, this group is just trivial. So it implies that all the surface cut algebras are derived equivalent. So of course, if you don't consider any puncture, it's not really interesting. I mean, it just say that, yeah, it was known from a long time. But here, I mean, the important point is that it works for And the second point here, so if you have G, if you assume that G is 0, so then the rank of this group is B minus 1, and in fact, this group is generated by these curves surrounding the boundary components. Right? You have B curves surrounding the boundary components, but somehow the last one is the combination of the other ones. So you just have to consider just B minus 1 subcurve. So it implies that the derived category of the surface cut algebra is determined by this generalized age invariant. So also you may have contour, so you may have generalized here. So at least this means that in the genus zero case, this invariant can really be computed easily. It's just the age invariant. Okay, so let me end with the first bad case. So with genus 1, so I should take genus 1, B equal 1, so just one boundary component, and I don't make any counter. And so here we can say something. So we start with two gradient triangulation, so two surface algebras, and we can fix A and B simple curves that generate the H1 of surface. So these two curves I have drawn, for instance, in red in my picture, so A and B. And what I can just easily compute is D of A and D of B, and D prime of A, D prime of B. And in fact, you can translate the condition like this, that this algebras are very equivalent even on if the great common divisor of EA and BB is the same as different A, different B. So, yes, but somehow, so here it's kind of nice, but yeah, I don't think that this book So here we have three different algebras, which are not directly equivalent. And actually, these algebras, they are gentle algebras, and they have the same AJ invariant. So, yeah, it was quite easy answer to an open question. I mean, it was not known that these algebras were not directly equivalent. So, okay. So, thank you very much.
Any questions?
Do you know how your ratings are related with the stability conditions?
No, not at all. They are nice. No, I don't know.
You sort of throw that and doing some of the things to more general diameters.
Yeah, I was planning actually.
Would you maybe repeat this?
Yeah, so he
question?
asked whether we could generalize this not for triangulation, but maybe diagonal configuration, like in Robert's law. And yeah, I would hope that it's possible. I mean, this would be something to check, but yeah, I think it should work the same way because I mean the main point is really because you have a kind of complex with this set Q2, Q1, and Q0 as in Robert's talk, and it's exactly the same. I mean, and the homology of this complex is the H1 of the surface and everything. So I guess it should work.
Any other questions? Oh, no?
Is there a way to recover the grading in the test algorithm?
This I don't know. Yeah, it's a good question. I mean, I just think about different mutations, so somehow I totally forgot to use algebra. But maybe we can do something about this grading because I don't know, but this would be interesting.
I think your last theorem could work for higher genus, genus larger than 1.
Yeah.
The last theorem.
So I don't think it works. So yeah, this one.
I mean, it may be an analog.
No. It just, I mean, in the proof, we use really, so first, it's not so the mapping class group of this surface is kind of easy to understand. It's just a central extension between Z and SL2 of Z. So it's not that bad. And there is a kind of miracle here, which is, I think, really specific to this case. That in fact, so this map EGAR, well, it does not factor through H1, but almost. And well, everything is in this almost. But then somehow, at the end, what you have to understand is just the action of. So H1 here is Z2, and you just have to understand the action of SL2Z and Z2, which is something really simple. So yeah, in well, maybe